Hello everyone, I'm Chakraborty from UC San Diego. I'm here to describe the importance and the far-reaching consequences of the findings we reported in Science this week. We addressed several outstanding issues in planetary science through this publication. Most importantly, we proposed a chemical recipe based on the results of laboratory simulation experiments of forming rocks from gases and addressed the question, what happened 4.6 billion years ago at the beginning of our solar system? Before going to details, I would like to create a background here to put all of us in the same page. Our solar system formed from a cloud of gas and dust called solar nebula and evolved to this beautiful planetary system we see today. From the gaseous nebula, we have rocky planets and asteroids. The question is how these rocks formed. The clue we get from the meteorites, the rocks from the asteroid belt between Mars and Jupiter. This paper is on oxygen isotopes. So let us talk about oxygen. Oxygen is the third most abundant element in the universe after hydrogen and helium. It is also the major element in all the rocks. Oxygen is everywhere. Therefore, we should care about it. Oxygen has three stable isotopes. 16 oxygen is the major one with abundance of more than 99%. 17 and 18 oxygens are the minors. When all three isotopes are plotted in a single diagram, we call it oxygen 3 isotope plot. Like this, where the ratio of 18 to 16 is in x-axis and 17 to 16 in y-axis. In this diagram, if we put the composition of Earth, Mars, and Moon, they follow a slope of 1/2 line, which can be explained by simple physics based on mass of the isotopes. The x-axis is the ratio of 18 to 16, as I said. 18 and 16 are apart by 2 mass units. Similarly, there is only 1 mass unit difference between 17 and 16 of y-axis. Therefore, 2 units of change in x-axis would result in 1 unit change in y-axis, and hence the slope half. The isotopic distribution over slope half line is normal and expected, and called mass-dependent fractionation. In this plot, the ocean water is at 0, 0. Rain and clouds are here, negative. Rocks are here, but all are over a slope of half line. You see, Mars and Moon are again here over slope half line. So this is the beauty of oxygen isotope. Everything lies so nicely in a known physics. In the same diagram, when meteorites are plotted, they don't look like that of the other things we know. They are in a slope of 1 line. When the slope half rule is not followed, this is called mass independent or anomalous. Therefore, the meteorites are anomalous in respect to oxygen isotopes. This is oxygen isotope puzzle for last 40 years since its discovery in 1973. An element so abundant should not be so heterogeneous. Again, the question is how these rocks form so that it has so different oxygen. The way we understood that does not go hand to hand with oxygen. The commons say if we want to understand the evolution of our solar system, we should understand the oxygen first. To answer this question, we simulated a gaseous environment of the nebula inside a reaction chamber and formed solid particles from gases as that happened in the nebula. Here is a real simulation, and what happens inside the chamber in an environment of oxygen and hydrogen, we generate a vapor plume of silicon monoxide with the use of an intense laser beam and oxidize that to form particles. The white particles that form through gas-phase reaction you see here. We collected these white particles and performed a lot of experiments and determined that to be SiO2, the simplest form of silicate rock. We also measured the oxygen isotopic ratio of these rocks by laser fluorescence technique using a mass spectrometer. We found that oxygen isotopes in the rocks follow a mass-independent distribution represented by this blue line. Further analysis indicates that the silicates in these experiments form in several different pathways, and OH oxidation is one of them. The red line here follows slope 1 distribution as that of the meteorite. At this point, you may be wondering what new about it. We all know OH oxidizes everything. It is the atmospheric detergent. The discovery is SiO reacting with OH forms SiO2 is a special kind of oxidation reaction. Forms and vibrationally activated complex SiOOH star before stabilization. Symmetry detects the isotopic distribution of the final product and generates mass-independent signature. In this case, slope 1 as that of meteorites. Therefore, our chemical recipe of the solar system is OH oxidation in the inner part of the solar nebula at the early stage. Astrophysical observations detected SiO molecules in other stellar systems. Spitzer telescope discovered the huge presence of OH in the nebular disk. All these together present a best-case scenario of silicate formation via OH reaction, which produced this distinct oxygen-isotope signature in meteorites. This is a very important finding which shows a process of rock formation in the gaseous nebula and addresses the oxygen isotope puzzle. This is the simplest first step. More complex mineral formation needed to be studied and would follow through. Thank you for your attention.